Hey everyone, we're going to pick up in section 7.2 and we are going to talk about confidence intervals for the next week or so. We're going to start off with a confidence interval per proportion. We use a proportion when we have some kind of categorical variable and want to summarize that. So for instance, if you surveyed 100 people and 24 of them believe in ghosts, the estimated proportion would be 24 divided by 100 or 0.24, and that's a way to summarize categorical variables. The next thing we're going to do is confidence intervals for means, and that'll have different notation. Okay, so confidence interval is a way to estimate a proportion from the population. So in general, we always have data as a sample, and we want to estimate a population proportion. So the notation that we use is P, meaning population proportion. And that's what we want to estimate. In general, we don't have all the information from the population, so we go out and we take a sample and we calculate a sample proportion, and that's P hat, so P with the caret over it. So this is a sample proportion. And you estimate that by taking the count that follow a certain characteristic. So above it would be 24 people believe in ghosts. We call that X. And then we divide by N, which is our sample size. So in the above example, it would be 24 divided by 100. That's how we calculated P hat from the sample, 0.24. Okay, and then Q hat is always 1 minus P hat. So if we know P hat, then Q hat's just 1 minus that. So Q hat in this example would be 1 minus 0.24, which would be 0.76. Okay, so in our formulas, we're always going to use proportions rather than confidence intervals. And proportions rather than percent. We are going to be calculating confidence intervals. And we're going to do this for the next couple weeks. A confidence interval always has what we call a point estimate. That's just the value that we get from our data. And in this case, for proportion, the point estimate would be P hat. Okay, so P hat should go there in that blank spot. And P hat would be a point estimate. And a point estimate is always an estimate of the parameter. So our sample proportion, so the proportion of 0.24, that's an estimate of the population proportion that believe in ghosts. However, we know that if we took a different sample, we maybe get a different sample proportion. And so our confidence interval incorporates that uncertainty. So a confidence interval is an interval that gives a lower bound and an upper bound for where we fall the true proportion lies. Because we know if we took another sample of 100 adults from the population and asked them if they believed in ghosts, we'd get something different than 0.24. And because there's uncertainty in our estimate of P hat, we like to create an interval around that. And then we're confident that that interval would contain the true proportion of adults that believe in ghosts. And a confidence interval, we need to decide on what we call a confidence level. Could be any percentage, but 90, 95, and 99% are the most common confidence levels. And but you can do an 80%, a 50%, but we generally like to have a high percentage or high confidence level in our confidence interval. Okay, so when you calculate a confidence interval, you end up with a lower bound and an upper bound. And suppose we have a confidence interval for P that goes between 0.381 and 0.497. And suppose this is what we call a 95% confidence interval. We could say that we're 95% confident that P falls within that interval, so between 0.381 and 0.497. Okay, and so just a little vocabulary. A critical value is the z-score that comes from the normal table and correlates with the formula for a confidence interval. And so every confidence level has a z-score, and we can look that up, but we usually, since we have common ones, I'll just give you the values for those common ones. But if we wanted to look up, say, a z-score that corresponds to the middle 95% of the data, that means in the tail I would have 2.5% to the left, 2.5% to the right, and I can look up either 0.975 or 0.025. And so I can do that on my calculator real quick. I can go to inverse norm, and type in 0.975, and that gives me a value of 1.96. And that's our critical value when we calculate the confidence interval by hand. And so this value here is 1.96. And the notation for this is a little bit confusing, and I'm going to just stick with what the book uses. The book uses this z alpha over 2 subscript, and for alpha equal 0.05, that's where we got the 0.025 in either tail. That represents a 95% confidence interval. And I know that's a bit confusing, and so I'm just going to give you the values for the critical levels. So a 90% confidence interval, what you would use in your formula that would correspond to an alpha level of 0.10, and then a critical value, we use 1.645. It doesn't really matter if you round it down or up, but to 3 digits is 1.645. And then we went over the 95%. I used the calculator for that. So 99%, our alpha level 0.01. And we use a critical value of 2.58. Okay, so those come from the normal table. We could have gotten both of those by looking at the normal table. Those are the common ones, and where they come into play is your formula right here. So if it's a 95% interval, you would use 1.96 right here. If it's a 99%, you would use 2.58 for this value right here. So this is just one value that we stick in the number for. Okay, so if you remember, the point estimate is p hat. And so a confidence interval is usually broken up into 2 parts. P hat is what would go in this blank spot here. That's the point estimate. And the other part is our margin of error. That gives us a little cushion because we know that our p hat's going to be off a little bit. So we add and subtract our margin of error. And the formula for the margin of error is right here. And we'll do some examples using that formula. It's fairly easy to do. And then for a confidence interval, remember it's an interval, so we have a lower bound and an upper bound. We take our point estimate, we add and subtract our margin of error. And so these formulas are the same because the error formula is given up here. So the whole formula is p hat plus or minus our critical value right here times this formula right here, which is known as the standard error. Okay, for any confidence interval to be valid, there's 3 conditions. We have to have a simple random sample. N times p hat, so the little caret above there has to be greater than or equal to 10. And n times q hat, I can't type that in, so I'm just going to write hat there, has to be also greater than or equal to 10. So it's a sample size requirement. And then also there has to be a fixed number, we'll just say fixed n. So you have a fixed sample size. So those are the three requirements for the confidence interval to be valid. The confidence interval formula is p hat plus or minus your margin of error. So you get a lower bound and then an upper bound. So let's go ahead and just jump right in and do a problem. So an important issue facing Americans is the large number of medical malpractice lawsuits and the expenses they generate. In a study of 1,228 randomly selected medical lawsuit practices found that 856 of them were later dropped or dismissed. Okay, so let's write down the things that we are given here. We are given n. This is n right here. And then we are also given x, the number of lawsuits. And then we want to construct a 99% confidence interval for the proportion of medical malpractice suits that are dropped or dismissed. And then the follow-up question. Okay, so I'm just going to jump down here. We're going to do this on the calculator as well as by hand. If you're going to do it by hand, the first thing you need to do is calculate p hat. That's your sample proportion. And so my p hat is equal to x, which was 856, divided by n, which is 1,228. And that's equal to, and you should take things to 3 digits, so we'll take the to 0.697. So 69.7% were successfully dropped. I think that's the sample proportion we're looking for. Compute the margin of error. Use your table on the previous page to get the value of z. So the previous page for 99% would be, my value for z would be 2.58. And that's what goes in the formula right here. So 2.58 goes into that formula there. Okay, so computing the margin of error, that's just that first equation right here. So I take 2.58 square root p hat, q hat, and n. Okay, so my margin of error is equal to 2.58. And then I take 0.697 times 0.303 divided by 1228. And that's equal to 0.0338. Okay, so that's my margin of error. To compute the confidence interval, I just take my p hat, so 0.697, plus or minus my margin of error, so 0.0338. Okay, because I'm just using this formula right here, p hat plus or minus the margin of error. And so that gives a lower bound of 0.663 and an upper bound of 0.731. I add and subtract this number here to 0.697. Okay, with that I'm going to end this video and we'll pick it up on the next video.